Tonight, we're going to confront one of the strangest ideas in all of physics. The idea that empty space is not empty. That even if you removed every atom, every particle, every trace of matter and radiation from a region of space, something would still be there. Not matter, not energy in any ordinary sense, but something. Something that can push metal plates together in a laboratory. Something that slightly shifts the color of light emitted by hydrogen atoms. Something that physicists have measured with extraordinary precision. And here's the part that will really challenge you. The way physicists describe what's happening involves entities called virtual particles. But virtual particles are not what most people think they are. They're not tiny objects flickering in and out of existence like fireflies in the dark. The truth is far stranger and far more interesting than that. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you understand. Nothing. Empty space. A vacuum. Take a box. Remove everything from it. Pull out all the air, every molecule of nitrogen, oxygen, carbon dioxide, water vapor. Remove every dust particle, every stray atom, every photon of light. Cool it down to as close to absolute zero as you can get. Shield it from every external influence. What's left inside that box? Your intuition says nothing. Absolutely nothing. Just empty space. A void. The absence of everything. And for most of human history, that answer would have been considered correct. The greatest minds who ever lived would have agreed with you. Empty space is empty. There's nothing there. End of discussion. But here's the thing. That answer is wrong. Not slightly wrong. Not technically wrong in some obscure way that only matters to physicists doing exotic calculations. It's fundamentally wrong. What's inside that box, even after you've removed every single particle of matter and every photon of radiation, is one of the most complex, dynamic, physically active things in the entire universe. And understanding why is going to take us on a journey through some of the deepest ideas in modern physics. To understand why empty space isn't empty, we first need to understand how humans have thought about empty space throughout history. Because our ideas about nothing have changed dramatically over the centuries, and each change revealed something profound about the nature of reality. The ancient Greeks argued about the vacuum for centuries. Aristotle, one of the most influential thinkers in history, flatly denied that a true vacuum could exist. His reasoning was actually quite logical given what he knew. He observed that objects fall through air more quickly than they fall through water. The thinner the medium, the faster things move through it. So Aristotle reasoned if you had a true vacuum, a medium with zero resistance, objects would move through it infinitely fast. Since nothing can move infinitely fast, a true vacuum must be impossible. Nature, he declared, abhors a vacuum. This phrase became one of the most famous in the history of science, and it dominated Western thinking about empty space for nearly 2,000 years. Scholars, theologians, and natural philosophers all accepted it as established wisdom. The void was impossible. Space must always contain something. Not everyone agreed. Democritus and his followers, the atomists, believed that the universe was made of tiny indivisible particles, called atoms moving through empty void. They needed the void to exist because without empty space between atoms, nothing could move. Everything would be frozen in place, locked together with no room to shift or rearrange. Without empty space, there could be no change, no motion, no life. The atomists were remarkably close to our modern picture in many ways, but they lost the argument. Aristotle's influence was too strong, his authority too deeply embedded in the intellectual traditions of the ancient world and the medieval scholars who inherited them. For centuries, the idea that a true vacuum could exist was considered almost heretical in European intellectual tradition. It wasn't until the 1600s that experiments start to settle the debate. In 1643, an Italian physicist named Evangelista Torricelli performed a famous experiment. He filled a glass tube about 3 feet long with mercury, sealed one end, and inverted the tube into an open dish of mercury. The mercury in the tube fell partway, leaving a gap at the top of the sealed end. What was in that gap? There was no air. There was no mercury. It appeared to be empty space, a vacuum right there in a laboratory for anyone to see. This was revolutionary. Torricelli had apparently created what Aristotle said was impossible, a region of true emptiness. The space above the mercury column became known as the Torricellian vacuum, and it sparked intense debate across Europe. Was it truly empty? Or was there some invisible substance filling it? Some philosophers insisted that an invisible material must be present, because true emptiness was unthinkable. Others saw Torricelli's experiment as proof that the void was real. The debate raged for years, drawing in some of the finest minds in Europe. A few years later, in 1654, a German scientist named Otto von Guericke performed an even more dramatic demonstration. He placed two large copper hemispheres together and pumped the air out of the space between them, using a vacuum pump he had invented. The hemispheres were held together so tightly by the pressure of the surrounding atmosphere that two teams of horses, 8 on each side, couldn't pull them apart. This was a vivid public demonstration that a vacuum could be created and that it had real physical consequences. The absence of air inside the sphere meant the atmospheric pressure outside had nothing to push against, and the force was enormous. These experiments seemed to prove that empty space could exist. You could create regions with no matter in them. The vacuum was real, and for the next few centuries, that's essentially how physics treated empty space. It was a stage, a background, a container in which things happened, but which had no properties of its own. Matter existed in space. Forces acted through space. Light traveled through space, but space itself was just there. Passive, inert, empty. Isaac Newton formalized this picture in his laws of motion and his theory of gravity. In Newton's universe, space was absolute. It existed independently of the objects within it. It was infinite, uniform, and featureless. You could remove everything from a region of space, every particle, every force, every influence, and what remained was pure mathematical space. A coordinate grid extending in all directions, empty, quiet, and dead. This picture worked extraordinarily well for over 200 years. Newton's mechanics could predict the motions of planets, the trajectories of cannonballs, the behavior of gases, the oscillations of pendulums. Engineers could build bridges and machines using Newton's laws. Astronomers could predict eclipses, calculate orbits, and discover new planets based on gravitational perturbations. The framework was so successful, so reliable, so consistently confirmed by experiment that there seemed to be no reason to question whether empty space might be anything other than empty. The vacuum was nothing, and nothing was boring. Nobody spent much time thinking about it because there was nothing to think about. Or so it seemed. But there were hints, even in the 1800s, that something might be off. When James Clerk Maxwell unified electricity and magnetism in the 1860s, he showed that light was an electromagnetic wave. Waves need a medium to travel through, or at least that's what everyone assumed. Sound waves travel through air. Ocean waves travel through water. So, what medium did light waves travel through? Physicists invented one. They called it the luminiferous ether. This ether was supposed to fill all of space, providing the medium through which light could propagate. It had to be incredibly rigid to support the high frequency of light waves, yet also perfectly transparent and undetectable by any direct measurement. It had to permeate everything, fill in every corner of the universe. The ether was, in a sense, the first hint that empty space might not be empty. If light could travel through a vacuum, and if light needed a medium, then the vacuum must contain something. But the ether turned out to be a dead end. In 1887, Albert Michelson and Edward Morley performed their famous experiment, trying to detect the motion of the Earth through the ether. They found nothing. No matter which direction they looked, no matter what time of year they measured, the speed of light was always the same. The ether didn't exist, or if it did, it was completely undetectable, which amounted to the same thing. Einstein's special theory of relativity, published in 1905, eliminated the need for the ether entirely. Light didn't need a medium. It was a self-propagating electromagnetic wave that could travel perfectly well through completely empty space. No ether required. No invisible substance filling the void. The vacuum was empty again. Just a void. Nothing there. But Einstein himself would help overturn this picture. Because in the early 1900s, a revolution was brewing in physics. A revolution that would fundamentally transform our understanding of everything, including what it means for space to be empty. That revolution was quantum mechanics. Quantum mechanics began with a problem about light. In 1900, the German physicist Max Planck was trying to explain how hot objects radiate energy. This was not an obscure problem. It was central to physics at the time. Every hot object glows. A piece of iron heated in a forge first glows red, then orange, then white as its temperature increases. The existing theories of the day predicted that a hot object should emit infinite energy at high frequencies, a result so absurd it was called the ultraviolet catastrophe. Planck found that he could fix the calculation by assuming that energy came in tiny discrete packets, which he called quanta. He didn't fully understand why this worked. He thought it was a mathematical trick, but it turned out to be one of the most important discoveries in the history of science. Over the next few decades, physicists built on Planck's insight to develop a complete theory of the microscopic world. Einstein showed in 1905 that light itself comes in quanta, packets of energy we now call photons. Niels Bohr proposed that electrons and atoms can only occupy certain discrete energy levels, jumping between them by absorbing or emitting photons. Louis de Broglie suggested that not just light, but all matter has wave-like properties. Erwin Schrödinger wrote down a wave equation that describes how quantum states evolve over time. Werner Heisenberg developed a matrix formulation that captured the same physics in a different mathematical language. And along the way, physicists discovered something deeply unsettling about the nature of reality. They discovered that particles like electrons behave as both particles and waves. They discovered that certain properties of particles, like their position and momentum, cannot both be known precisely at the same time. This is the Heisenberg uncertainty principle, one of the most important ideas in all of physics. The uncertainty principle isn't a limitation of our measuring instruments. It's not that we lack sufficiently precise tools. It's a fundamental property of nature itself. At the quantum level, reality is inherently uncertain. A particle doesn't have a definite position and a definite momentum simultaneously. These properties are fuzzy, smeared out, defined only within ranges. And the more precisely you know one, the less precisely you can know the other. This uncertainty has consequences for empty space. Because here's the key insight. If you could have a region of space that was perfectly, completely, absolutely still, with zero energy and zero activity of any kind, you would know everything about that region with perfect precision. You would know that the energy is exactly zero. You would know that nothing is happening. But the uncertainty principle says you can't know things with perfect precision. There must always be some residual uncertainty, some irreducible fuzziness. And that means even the emptiest possible state of space cannot be perfectly still. There must be some minimum level of activity, some irreducible quantum jitter that can never be removed no matter what you do. This is a profound idea. It means that the vacuum, the emptiest state of space, is not truly empty. It has a minimum energy. It has fluctuations. It has activity. Not because something was put there, but because the laws of quantum mechanics require it. Perfect emptiness would violate the uncertainty principle. So perfect emptiness cannot exist. But to really understand what's going on, we need to take one more step. We need to move from quantum mechanics, the physics of particles, to quantum field theory, the physics of fields. And this is where the modern understanding of the vacuum truly begins. In everyday language, we talk about particles, electrons, photons, quarks, the building blocks of matter and light. We imagine them as tiny objects, little balls or points zipping around through space. This picture works well enough for many purposes, but it's not what modern physics actually says. Modern physics says that the fundamental objects in the universe are not particles, they are fields. A field is something that has a value at every point in space and time. You've encountered fields before, even if you didn't call them that. Temperature is a field. At every point in a room, there's a temperature. Some spots are warmer, some are cooler, but there's a value everywhere. Pressure is a field. The wind is a vector field, with both a magnitude and a direction at every point. Gravity is a field. At every point near Earth, there's a gravitational pull with a specific strength and direction. Quantum field theory says that the entire universe is permeated by fields. There's an electron field that fills all of space. There's a photon field, also called the electromagnetic field, that fills all of space. There's a quark field, a neutrino field, a muon field. For every type of particle that exists, there's a corresponding field that extends through the entirety of the universe. These fields are always there. They don't come and go. They don't appear and disappear. They're permanent features of reality, as fundamental as space and time themselves. What we call a particle is actually an excitation of one of these fields. Think of a calm lake on a perfectly still morning. The surface of the lake is like a quantum field in its lowest energy state. It's there, it's real, it stretches from shore to shore, but nothing dramatic is happening. The surface is flat, quiet. Now drop a stone into the lake. A ripple forms. That ripple is a localized disturbance in the surface of the lake, a bump of energy traveling across it. The ripple isn't a separate thing from the lake. It is the lake disturbed. It's the lake carrying energy from one place to another. In quantum field theory, a particle is like that ripple. It's a localized excitation, a bundle of energy in the field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Every particle you've ever heard of is a ripple in its corresponding field, and every one of those fields fills the entire universe. This might seem like just a different way of saying the same thing, but it changes everything. Because if particles are excitations of fields, and fields fill all of space, then even when there are no particles, the fields are still there. The lake is still there, even when there are no ripples. The electron field is still there, even when there are no electrons. The electromagnetic field is still there, even when there are no photons. Space is never truly empty, because the fields that give rise to everything in the universe are always present everywhere. Now, here's where the uncertainty principle comes back in. Remember, quantum mechanics says you can never have a state of perfect stillness. There must always be some residual fluctuation. Apply this to the quantum fields that fill all of space, and you get a remarkable result. Even in the vacuum state, even when a field is in its lowest possible energy configuration, it's still fluctuating. The field is still jittering, still vibrating at a minimum level that can never be reduced to zero. This is what physicists call the quantum vacuum. It's not empty. It's the state where all quantum fields are in their lowest energy configuration. It's the quietest possible state of reality. But quiet is not silent. The fields are still there, still fluctuating, still doing something. And those fluctuations, as we'll see, have real measurable consequences. This idea actually has a simple analogy in basic quantum mechanics. Consider the simplest quantum system, a quantum harmonic oscillator. This is just a particle trapped in a bowl-shaped potential, like a marble in a curved dish. In classical physics, the lowest energy state of this system is the marble sitting perfectly still at the bottom of the bowl. Zero energy, zero motion. But in quantum mechanics, the uncertainty principle forbids this. The particle cannot sit perfectly still because that would mean, its position and momentum both exactly. So even in its lowest energy state, the quantum harmonic oscillator has some energy. This is called the 0 point energy. The particle is always jiggling, always moving, even in the ground state. Quantum fields work the same way. Each field at each point in space behaves like a quantum oscillator, and each one has 0 point energy. The vacuum, the ground state of all these fields together, has an enormous number of these tiny minimum energies all added up. Let me make this more concrete. Imagine you could zoom in on a tiny region of what you think is empty space. At the scale of everyday life, it looks empty. There's nothing there. But if you could somehow see the quantum fields, you'd see something very different. You'd see the electromagnetic field gently rippling, never perfectly still. You'd see the electron field fluctuating, the quark field, the neutrino field, all of them vibrating at their minimum level. Not producing particles exactly, not in the way we usually think of particles as things you can detect and measure, but fluctuating nonetheless. The fields are restless. They can't help it. The laws of physics demand it. These fluctuations are sometimes described in popular science as particles popping in and out of existence. You've probably heard this before. The idea that empty space is teeming with virtual particles, pairs of matter and antimatter particles appearing from nothing, existing for a brief instant, and then annihilating each other and vanishing. It's a vivid image. It's dramatic. And it's deeply misleading, as we'll explore later. But the underlying idea that the vacuum is not quiet, that there's activity even in the emptiest state of space, that part is correct. The vacuum state is actually a precisely defined concept in quantum field theory. It's the state of lowest energy. It's denoted by physicists with a specific mathematical symbol. This state has exact mathematical properties. It's the state with no particles present, no excitations above the ground state, nothing you could detect as a real particle in any experiment. And yet, this state is not nothing. The fields are present. They have 0 point energy, the minimum energy required by the uncertainty principle. And while certain field quantities average to zero, the fluctuations around that average are not zero. The fields are there. They're fluctuating. They're real. This is a radically different picture from the one Newton or even Einstein had. In Newton's universe, empty space was truly empty, a featureless void. In quantum field theory, empty space is the ground state of an enormously complex system of interacting fields. It is the quietest the system can be, but it's never truly quiet. It's alive with quantum activity. And here's what makes this more than just abstract theorizing. These vacuum fluctuations, these residual jitters of quantum fields in their lowest energy state, they have physical effects. Real, measurable, experimentally confirmed physical effects. They push metal plates together. They shift the energy levels of atoms. They modify the way electric and magnetic fields behave. The vacuum isn't just theoretically active, it's experimentally demonstrably active. This should strike you as extraordinary. It means that what we call nothing, the best approximation of empty space we can create, is not nothing at all. It's something. Something with energy, with activity, with measurable physical consequences. The ancient Greeks debated whether the void could exist. Modern physics has an answer. It depends on what you mean by the void. If you mean a region with no particles, yes, that can exist. We create such regions in laboratories all the time. But if you mean a region with truly nothing in it, no fields, no energy, no activity of any kind, then no. That cannot exist. The quantum fields are always there, and they always fluctuate. There's a beautiful irony in this. Aristotle said, nature abhors a vacuum. He was wrong about the reasons, but in a deep sense, he was right about the conclusion. Nature does abhor a true vacuum, a state of absolute nothingness. The laws of quantum mechanics forbid it. Even the emptiest possible state has structure, energy, and activity. Complete nothingness is not just rare, it's impossible. This realization has implications that stretch far beyond abstract physics. It touches on some of the deepest questions we can ask about reality. What is the universe made of? What is the fundamental nature of matter and energy? What does it mean for something to exist? If the vacuum isn't empty, if space itself is a dynamic physical thing with properties and behaviors and measurable effects, then our everyday intuition about what's real and what isn't needs serious revision. You might be sitting in a room right now, looking at the space between you and the wall. It looks empty. There's air there, sure. But if you remove the air, you'd expect nothing to remain. Yet, Quantum field theory tells us that something does remain. The electron field is there. The electromagnetic field is there. Every quantum field in the standard model of particle physics is there, filling that space, fluctuating in its ground state, irreducible, fundamental, real. You can't see these fields, you can't feel them, but they're there, and their presence has consequences. Consider the electromagnetic field for a moment. When there are no photons present, when no light is traveling through a region of space, the electromagnetic field is in its vacuum state. But even in this state, the field is fluctuating. The electric and magnetic field strengths at any point are not exactly zero. They fluctuate around zero, sometimes slightly positive, sometimes slightly negative. On average, they cancel out. The average electric field in the vacuum is zero. The average magnetic field in the vacuum is zero. But the average of the square of these fields is not zero. The fluctuations are real. They carry energy. And they can interact with matter that happens to be nearby. This is why an electron in an atom doesn't behave quite the way simple quantum mechanics predicts. The electron isn't just interacting with the nucleus and with any other electrons in the atom. It's also interacting with the vacuum fluctuations of the electromagnetic field. These interactions are tiny, but they're measurable. And they shift the energy levels of the atom by small but precise amounts. We'll talk about this in detail later. But the point for now is that the vacuum has physical effects. It's not just a theoretical construct. It's an experimentally verified feature of reality. This brings us to a crucial question. If the vacuum has all this activity, if quantum fields are fluctuating even in their lowest energy state, then what exactly are these fluctuations? What's physically happening in empty space? And this is where we encounter one of the most misunderstood concepts in all of physics: virtual particles. You've almost certainly heard the term before. It shows up constantly in popular science books, documentaries, and articles about physics. The usual description goes something like this: empty space is teeming with virtual particles. These are particle-antiparticle pairs that pop into existence from nothing, live for a tiny fraction of a second, and then annihilate each other and vanish. They can do this because of the uncertainty principle, which allows energy to be borrowed from the vacuum for a short time, as long as it's paid back quickly. The shorter the time, the more energy can be borrowed. And so the vacuum is a seething foam of particles appearing and disappearing constantly. This description is colorful, it's intuitive, it creates a vivid picture in your mind of empty space as a fizzing, bubbling, particle filled thing, and elements of it capture something real about the physics. But as a description of what's actually happening, it's deeply problematic. It confuses a mathematical tool with physical reality. It takes a metaphor and mistakes it for a literal description of nature. Understanding what virtual particles actually are, what they really represent in the mathematics of quantum field theory, and why the popular picture is misleading. That's one of the most important things we can do to genuinely understand modern physics. Because the truth about virtual particles is more subtle, more interesting, and more beautiful than the cartoon version. And getting it right changes how you understand not just the vacuum, but reality itself. The vacuum is not empty. Something is happening in the quietest state of space. But what's happening is not tiny particles flickering in and out of existence like fireflies. What's happening is that quantum fields, the most fundamental objects in the universe, are doing what quantum fields always do. They're fluctuating. And those fluctuations have consequences. Understanding exactly how physicists describe those consequences and why the language of virtual particles entered the picture is where we're going next. And trust me, the real story is far more fascinating than the myth. So now we know that empty space is not empty. The vacuum is the ground state of quantum fields that fill every point in the universe. These fields fluctuate even in their quietest possible state. And physicists have developed an incredibly precise mathematical framework, quantum field theory, to describe how these fields behave and interact. But here's where things get tricky. Because when physicists use this framework to calculate things, when they work out the probability that two electrons will scatter off each other, or that a photon will be absorbed and re-emitted by an atom, the mathematics involves something called virtual particles. And the name is deeply misleading. The word particle makes you think of a thing, tiny object, something with a location, a trajectory, something you could, in principle, see or detect. The word virtual suggests it's almost real, like virtual reality, a convincing imitation of the real thing. Put the two words together and your brain naturally constructs an image. Tiny, almost real particles, little ghostly objects that almost exist, flickering in and out of being somewhere in the space between real particles. And that image, as intuitive and vivid as it is wrong. To understand what virtual particles actually are, we need to talk about how physicists calculate things. Because virtual particles don't live in space, they live in equations. They're features of a mathematical method, not features of the physical vacuum. And the only way to see this clearly is to understand the method. When physicists want to calculate what happens when particles interact, when two electrons repel each other, for example, they use a technique called perturbation theory. The idea behind perturbation theory is straightforward. You start with something you know how to solve exactly, and then you add small corrections. If the corrections are small enough, you can calculate them one at a time, each one refining your answer a little more. Here's an analogy. Imagine you want to predict the path of a ball rolling across a table. If the table is perfectly flat and smooth, you can calculate the path exactly. The ball rolls in a straight line. Simple. But real tables aren't perfectly flat. They have tiny bumps and dips. So you start with the straight line path and then add corrections. The first correction accounts for the biggest bump. The second correction accounts for the next biggest bump. Each correction makes your prediction a little more accurate. If the bumps are small, the first few corrections give you a very good answer, and you can stop. Perturbation theory works the same way. You start with free particles, particles that aren't interacting with anything. You know, exactly how free particles behave. A free electron just moves through space at a constant velocity. A free photon just travels at the speed of light. These are simple, solved problems. Then you add the interaction as a small correction. The first correction gives you the simplest possible way the particles could interact. The second correction gives you a more complicated interaction. The third gives you an even more complicated one. And so on. Each correction involves more complex mathematics, but gives you a more accurate answer. The beauty of this approach is that if the interaction is weak, meaning the corrections are small, you can stop after just a few terms and still get an incredibly accurate answer. You don't need to sum up the infinite series. The first few terms are enough. For electromagnetism, this works spectacularly well because the electromagnetic interaction is relatively weak. In quantum field theory, The strength of the interaction determines how quickly these corrections get smaller. For electromagnetism, the relevant number is called the fine structure constant, which has a value of approximately 1 divided by 137. Because this number is much less than 1, each successive correction in the perturbation series is roughly 137 times smaller than the one before it. This means the first correction gives you a good answer. The first 2 corrections give you a very good answer. The first 3 give you an excellent answer, and so on. The series converges quickly, which is why QED can make such precise predictions. Now, here's where Feynman diagrams come in. In the late 1940s, Richard Feynman developed a brilliant visual tool for organizing the terms in these perturbation series. Each term in the series, each correction to the calculation, can be represented by a picture. These pictures are called Feynman diagrams. A Feynman diagram is not a picture of what's physically happening in space. This is the single most important thing to understand about Feynman diagrams, and it's the thing that causes the most confusion. A Feynman diagram is a bookkeeping device. It's a visual way of keeping track of the mathematical terms in a calculation. Each diagram represents a specific mathematical expression, a specific integral that contributes to the final answer. The diagram tells you which integral to write down and how to evaluate it. That's all it does. Let me describe what a Feynman diagram looks like so you can understand the pieces. In a typical Feynman diagram, you have external lines and internal lines. The external lines represent real particles. These are the particles that exist before the interaction begins and after it ends. They're the particles that travel through space, hit detectors, and get measured by experimenters. If you're calculating the scattering of 2 electrons, the external lines are 4 electron lines, 2 coming in representing the 2 electrons before they interact, and 2 going out representing the 2 electrons after they interact. The internal lines are different. They connect the external lines inside the diagram. They represent mathematical terms in the calculation that describe how the interaction proceeds. In the simplest diagram for electron-electron scattering, there's one internal line connecting the 2 electron lines. This internal line is labeled as a photon. It represents a term in the mathematics that describes the electromagnetic interaction between the 2 electrons. And here's the critical point. That internal line, labeled as a photon, is what physicists call a virtual photon. It is not a real photon. It does not travel through space. It does not carry a definite amount of energy and momentum in the way that a real photon does. It is a line in a diagram that represents a term in a mathematical expression. It's a piece of the calculation. Let me say that again because it's important. A virtual particle is a line in a Feynman diagram. A Feynman diagram is a visual representation of a term in a perturbation series. A perturbation series is a mathematical method for calculating the probability of a physical process. The virtual particle exists in the mathematics. It does not exist as an independent physical object in space. Now, why is the internal line different from the external lines? What makes a virtual particle different from a real particle in the mathematics? The answer has to do with something called the energy-momentum relation. Every real particle in physics obeys a specific relationship between its energy and its momentum. For a particle with mass, this relationship comes from Einstein's special relativity. The energy squared equals the momentum squared times the speed of light squared plus the mass squared times the speed of light to the 4th power. This is the famous equation that simplifies to E equals mc squared when the particle is at rest with zero momentum. Real. Particles always obey this relation. Always. A real electron always has energy and momentum that satisfy this equation for the electron's known mass. A real photon, which has zero mass, always has energy equal to its momentum times the speed of light. These relationships are not approximate, they're exact. Every real particle that has ever been detected obeys its energy momentum relation precisely. Virtual particles do not obey this relation. In the mathematics of Feynman diagrams, the internal lines can carry any combination of energy and momentum, including combinations that would be impossible for a real particle. A virtual photon can have mass even though real photons are massless. A virtual photon can carry energy and momentum in a ratio that no real photon could ever have. A virtual electron can have the wrong relationship between energy and momentum for its known mass. Physicists say that virtual particles are off-shell, meaning they're off the mass shell, the surface in energy momentum space where real particles live. Being off-shell is not something that happens occasionally or under special circumstances. It's the defining feature of virtual particles. Every virtual particle in every Feynman diagram is off-shell. If it were on shell, obeying the correct energy momentum relation, it would be a real particle, not a virtual one. This is not a minor technicality. It's fundamental to what makes virtual particles virtual. They violate the rules that real particles must follow. They carry impossible combinations of energy and momentum. And this is fine because they're not real particles. They're mathematical terms in a calculation. The rules that apply to real observable particles don't need to apply to intermediate mathematical quantities any more than the intermediate steps in a long division problem need to be meaningful numbers on their own. Here's another crucial difference. When you calculate a physical process using Feynman diagrams, you don't just draw one diagram. You draw all possible diagrams that connect the same set of external lines. For electron-electron scattering, the simplest diagram has one internal photon line, but there are more complex diagrams with two internal lines, three internal lines, four, and so on. There are diagrams where the internal lines form loops. There are diagrams where virtual particles appear and disappear in pairs. The number of possible diagrams is infinite. Each diagram represents a mathematical term. The final answer, the probability of the scattering event, is the sum of all these terms. You add up the contributions from every possible diagram. The simplest diagrams give the largest contributions. More complex diagrams give smaller and smaller contributions. Because the fine structure constant is small, about 1 over 137, each additional layer of complexity reduces the contribution by roughly that factor. And here's what's essential. No single diagram represents what actually happens. The physical process is described by the sum of all diagrams. You can't point to one diagram and say, this is what the particles did. The particles didn't do any specific one of these things. All the diagrams contribute. All the virtual particles in all the diagrams contribute. The final physical result emerges from the sum of everything. It's as if you asked someone how they got to work, and they said, I took every possible route simultaneously, and the answer is the combined result of all of them. That sounds absurd in everyday life, but it's exactly how quantum mechanics works. The mathematical structure of quantum field theory requires summing over all possible intermediate processes, and the virtual particles are the labels we give to those intermediate processes. This is radically different from classical physics, where you can trace a definite path and say, the ball rolled this way. In quantum field theory, you sum over all possible intermediate configurations. The virtual particles in any single diagram are not things that happened. They're terms in a sum, components of a calculation, mathematical ingredients in a recipe that produces a physical prediction. Think of it this way. If you want to know the area of a complicated shape, you might break it into simpler pieces, calculate each piece, and add them up. The individual pieces are useful for the calculation, but they don't have independent physical significance. The area of the whole shape is what matters. The individual pieces are just a method for getting there. Virtual particles are like those pieces. They're useful components of a calculation. They help physicists organize and evaluate the mathematics, but they don't have independent physical reality. The physical reality is the final answer, the probability of the interaction, which emerges from summing over all possible diagrams with all possible virtual particles. Let me push this further because there's another layer of subtlety that matters. Even the choice of which virtual particles appear in the diagrams depends on how you set up the calculation. Different mathematical approaches to the same physical problem can involve different types of virtual particles. In the standard approach to QED, the interaction between two electrons is described in terms of virtual photons. The internal lines are photon lines. But there are other formulations of the same physics that don't use virtual photons at all. In one formulation called the Coulomb gauge, part of the interaction between electrons is described by an instantaneous potential, not by the exchange of any virtual particle. In another formulation, the interaction can be described using different mathematical objects entirely. The physical predictions are always the same, regardless of which formulation you use. The probability that the electrons scatter at a particular angle is the same number, no matter how you calculate it. But the virtual particles that appear in the intermediate steps are different. In one approach, you have virtual photons. In another, you don't. This proves that virtual particles are features of the mathematical method, not features of the physics. If they were real physical objects, they couldn't appear and disappear depending on how you choose to do the mathematics. Real things don't depend on your choice of calculation method. This is analogous to something you might encounter in everyday mathematics. If you want to calculate the distance between 2 points, you can use Cartesian coordinates, where you work with x and y values, or you can use polar coordinates, where you work with angles and distances from an origin. The intermediate numbers you calculate are different in each coordinate system. The x and y components of the displacement exist in Cartesian coordinates, but don't exist in polar coordinates. Instead, you have a radial distance and an angle. But the final answer, the distance between the 2 points, is the same regardless of which coordinate system you use. Virtual particles are like the coordinate components. They're useful for the calculation. They appear in one mathematical setup, but not in another. And the final physical result doesn't depend on which setup you choose. This is a strong indication that virtual particles are mathematical tools, not physical realities. Now, I want to be fair to the other side of this discussion because the relationship between virtual particles and physical reality is more nuanced than simply saying they're fake. The mathematics of quantum field theory is telling us something real about how nature works. The calculations that involve virtual particles give incredibly accurate predictions. The virtual particle language captures something genuine about the structure of quantum field interactions. It's not arbitrary or meaningless. When physicists say that two electrons repel each other by exchanging virtual photons, they're using a shorthand. What they mean is that the electromagnetic field mediates the interaction between the two charged particles. And when you calculate the details of this interaction using perturbation theory, the mathematical terms can be organized and visualized as the exchange of virtual photons. The field interaction is real. The force between the electrons is real. The mathematical representation in terms of virtual photon exchange is a specific way of describing that real interaction. The danger comes when people take the shorthand too literally. When they imagine tiny photon like objects literally flying back and forth between electrons. When they picture the vacuum as a sea of particles constantly popping into and out of existence like bubbles in boiling water. These images are vivid and memorable, which is why they're popular in science communication. But they create a false picture of what the physics actually says. The physics says that quantum fields interact, that fields mediate forces, that the vacuum is the ground state of these fields, that the ground state has physical consequences. All of this is true and important. The language of virtual particles is one way to describe these truths mathematically. But it's not the only way, and it shouldn't be taken as a literal description of tiny objects existing in space. Let me give you a concrete example to illustrate the difference between real and virtual particles. Imagine an experiment where two electrons are heading toward each other. They approach, they interact electromagnetically, they repel each other, and they fly apart at some angle. This is a real experiment that happens millions of times per second in particle accelerators around the world. Accelerators like the Large Hadron Collider at CERN in Switzerland or the older Stanford Linear Accelerator in California have performed these kinds of scattering experiments countless times. The results are recorded, tabulated, and compared with theoretical predictions. The agreement between experiment and theory is extraordinary. The two electrons before and after the interaction are real particles. They were created by some source, perhaps a heated filament or a radioactive decay. They travel through the accelerator guided by magnetic fields. They have definite energies and momenta that obey the energy-momentum relation. They hit detectors. They leave tracks in tracking chambers. They deposit energy in calorimeters. They can be photographed, measured, counted. They are as real as any physical object can be. Now, the interaction itself, what happens in between? In the Feynman diagram picture, you draw internal lines, virtual photons, virtual electron-positron pairs, more and more complex diagrams. But none of these internal lines correspond to something you can observe. You can't put a detector between the two electrons and catch a virtual photon in the act of being exchanged. It's not that your detector isn't sensitive enough, it's that the virtual photon is not an observable thing. It's part of the mathematical description of the interaction, not a physical object traveling from one electron to the other. If you did put a detector in between the two electrons, one of two things would happen. Either the detector doesn't register anything, in which case the electrons scatter as usual, or the detector does register a photon, but now you've changed the experiment. Instead of two electrons scattering, you now have two electrons emitting and absorbing a real photon. The photon the detector caught is a real photon, one that obeys the energy-momentum relation, one that traveled through space and hit your detector. The experiment has changed. The diagrams have changed. The mathematics has changed. You haven't caught a virtual photon. you've created a different physical process that involves a real photon. This is a deep and important point. Virtual particles cannot be observed, not because we lack the technology, not because they're too small or too fast, but because observation itself changes the physics. The moment you try to observe a virtual particle, you turn it into a real particle, and you're doing a different experiment. Virtual particles exist only as internal features of the calculation describing a specific process. They are, by their very nature, unobservable. There's another popular image that needs correcting. You've probably heard that the vacuum is filled with virtual particle antiparticle pairs constantly popping into existence and annihilating. Electron positron pairs appearing from nothing, existing for a fleeting moment, and then disappearing. This image is everywhere. It's in popular science books, documentaries, magazine articles, websites. It's one of the most widely repeated descriptions of the quantum vacuum. And it's misleading. What's actually happening is that the quantum fields are fluctuating in their ground state. The electron field fluctuates. The electromagnetic field fluctuates. These fluctuations are real in the sense that they have measurable consequences, as we'll see shortly. But they're not particle antiparticle pairs appearing and disappearing. That language comes from one specific way of mathematically decomposing the field fluctuations, a decomposition that uses the virtual particle formalism. It's the perturbation theory picture being taken literally. In a different mathematical formulation of the same physics, the vacuum fluctuations can be described without any reference to particles at all. You can describe them purely in terms of field configurations as fluctuations in the value of the field at each point in space. No particles popping in and out, just fields doing what fields do in their ground state, which is fluctuate. The particle language is not wrong in the sense that the calculations based on it give correct answers, but it's incomplete and misleading when taken as a literal picture of what's happening in space. The vacuum isn't full of tiny electron positron pairs flickering into existence like sparks from a fire. The vacuum is the ground state of quantum fields. The fields fluctuate, and one mathematical way to characterize those fluctuations is in terms of virtual particles. But that's a choice of description, not a revelation of tiny objects actually appearing and vanishing. So let me summarize clearly what virtual particles are and what they are not. Virtual particles are internal lines in Feynman diagrams. Feynman diagrams are visual representations of mathematical terms in perturbation theory calculations. Perturbation theory is a method for approximately calculating the probabilities of physical processes in quantum field theory. Virtual particles are mathematical features of this specific calculation method. Virtual particles are not tiny objects that pop in and out of existence in empty space. They are not almost real particles that exist for a very short time before disappearing. They are not borrowed energy from the vacuum. They are not things you could detect with a better instrument. They are not independently existing entities with locations and trajectories. Real particles travel through space. Virtual particles exist in equations. Real particles hit detectors. Virtual particles contribute to calculation terms. Real particles obey the energy-momentum relation. Virtual particles don't. Real particles are independent of how you choose to do the mathematics. Virtual particles depend entirely on the mathematical framework you choose. Real particles are features of the physical world. Virtual particles are features of our description of the physical world. This distinction matters not because virtual particles are useless. They're incredibly useful. The Feynman diagram technique, with its virtual particles, is one of the most powerful calculational tools in all of physics. It allows physicists to compute interaction probabilities with astonishing precision. It provides physical intuition about how different processes contribute to an interaction. It organizes enormously complex calculations into manageable visual pieces. Feynman diagrams and virtual particles are indispensable tools of modern physics. But tools are not the same as reality. A map is not the territory. A menu is not the meal. And virtual particles are not real particles. They are elements of an extraordinarily useful mathematical language that physicists have developed to describe how quantum fields interact. The language works brilliantly. The predictions it generates match experiments to extraordinary accuracy. But the specific vocabulary of that language, the virtual photons and virtual electron positron pairs, should not be confused with actual objects in the physical world. The physical reality is simpler and in many ways more beautiful than the virtual particle picture suggests. Quantum fields fill all of space. They are present at every point, in every direction, at every moment. These fields interact with each other according to specific rules encoded in the laws of physics. When two charged particles come near each other, their presence disturbs the electromagnetic field between and around them, and that disturbance affects both particles. This is what we call a force. The field mediates the interaction. No tiny objects need to fly back and forth. The field is right there, at every point between the particles, and the interaction happens through the field. When we calculate the details of this interaction using perturbation theory, the mathematics can be organized in terms of virtual photons. But the photons are a feature of the mathematical organization, not a feature of the field interaction itself. The field doesn't know about Feynman diagrams. The field just does what the equations of quantum field theory say it does. We invented the diagrams to help us solve those equations. So why does all this matter? Why should you care whether virtual particles are real objects or mathematical tools? Because the answer shapes how you understand the vacuum, how you understand forces, and how you understand some of the most profound phenomena in modern physics. The vacuum has real, measurable physical effects. Forces between particles are real, but the mechanism behind these effects is not tiny objects appearing from nowhere and vanishing into nowhere. The mechanism is quantum fields doing what quantum fields do, interacting, fluctuating, existing everywhere and always, even in their quietest possible state. And those measurable effects, the real physical consequences of the quantum vacuum, are what we're going to explore next. Because while virtual particles themselves are mathematical tools, the phenomena they help us calculate are absolutely real. Real enough to push metal plates together in a laboratory. Real enough to shift the energy levels of hydrogen atom by precisely calculable amounts that match experiment beautifully. Real enough to change the way we understand the universe. The vacuum is not empty. The fields are always there. And they have consequences that you can see, measure, and verify. That's where we're heading next. So we've established two important things. First, the quantum vacuum is not empty. It's the ground state of quantum fields that fill every point in space. And those fields fluctuate even in their lowest energy state. Second, virtual particles are not tiny objects popping in and out of existence. They're mathematical terms in a specific calculation method that physicists use to describe how fields interact. But now comes the part that makes all of this more than just abstract theory. Because the quantum vacuum, despite being the quietest possible state of the fields, has real, measurable physical effects. Effects that have been confirmed in laboratories. Effects that you can see in data, in numbers, in experimental results that match theoretical predictions to astonishing precision. The vacuum does things. And in this part, we're going to look at exactly what it does and how we know. Let's start with the most famous example, the Casimir effect. In 1948, a Dutch physicist named Hendrik Casimir made a remarkable prediction. He proposed that if you take two flat, uncharged, perfectly conducting metal plates and place them very close together in a vacuum, with nothing between them, no air, no radiation, no particles of any kind, the plates will be attracted to each other. They will feel a force pulling them together. Not because of gravity, not because of static electricity, not because of any magnetic field, but because of the quantum vacuum itself. Think about how strange this is. You have two metal plates. They're electrically neutral. There's nothing between them. In classical physics, there is absolutely no reason for these plates to attract each other. They're just sitting there in empty space. There's nothing to push them or pull them. The space between them is empty. Nothing should happen. But something does happen. The plates are pushed together by a measurable force. And the explanation lies in the quantum nature of the electromagnetic field. Here's how it works. Remember that the electromagnetic field fills all of space and fluctuates even in its ground state. These fluctuations can be thought of as having different wavelengths, different modes of vibration, similar to how a guitar string can vibrate at its fundamental frequency or at higher harmonics. A guitar string fixed at both ends can only vibrate at wavelengths that fit neatly between the two fixed points. The fundamental mode has a wavelength equal to twice the string's length. The next harmonic has a wavelength equal to the string's length. The next has a wavelength of 2/3 the string's length, and so on. Only certain wavelengths are allowed. Others are forbidden by the boundary conditions, the fact that the string is fixed at both ends. In open space, far away from any boundaries, the electromagnetic field can fluctuate at any wavelength. There's no restriction. All wavelengths are equally possible. Short wavelengths, long wavelengths, everything in between. The field fluctuates freely in all possible modes, and there are infinitely many of them. But between the two metal plates, the situation is different. The plates impose boundary conditions on the field. Conducting metal plates force the electromagnetic field to have specific values at their surfaces. The electric field component parallel to the plate surface must vanish at the surface of a perfect conductor. This means that between the plates, not all wavelengths of fluctuation are possible. Only certain wavelengths fit between the plates. Wavelengths that are too long to fit between the plates are excluded. The plates act like the fixed ends of a guitar string. Only certain standing waves can exist between them. Outside the plates, there's no such restriction. All wavelengths are still possible. So there are more possible modes of fluctuation outside the plates than between them. The fluctuations outside push inward from both directions. The fluctuations inside push outward. But because there are fewer modes inside than outside, the outward push from inside is weaker than the inward push from outside. The result is a net force pushing the plates together. This is the Casimir effect, a force that arises purely because the quantum vacuum fluctuations are altered by the presence of the plates. Nothing is exchanged between the plates. No particles fly back and forth. No energy is transmitted in any ordinary sense. The plates simply change the way the electromagnetic field fluctuates in the space between them, and that change in fluctuation produces a measurable force. Now, you might ask whether this has actually been measured. Can you really detect such a tiny force arising from the quantum vacuum? The answer is yes, but it took decades to do it, convincingly. Casimir made his prediction in 1948, but the force he predicted is extraordinarily small. For plates separated by a distance of about 1 micrometer, which is 1 millionth of a meter, roughly 100 the width of a human hair, the Casimir force is roughly equivalent to the weight of about 1/100th of a milligram acting on each square centimeter of plate area. That's incredibly tiny. To give you a sense of how small this is, it's roughly the weight of a few specks of the finest dust you can imagine. You need extremely flat, smooth plates, very precise distance control, and very sensitive force measurements to detect it. Any imperfection in the experiment, any stray electric charge, any vibration from a passing truck could completely overwhelm the signal you're looking for. Early attempts to measure the Casimir effect in the 1950s and 60s were inconclusive. The experiments were brutally difficult. The plates had to be brought incredibly close together without actually touching. Any dust particle, any surface roughness, any residual electric charge could overwhelm the tiny Casimir force. The technology of the time simply wasn't precise enough. It wasn't until 1997 that a definitive measurement was made. Steve Lamoureux, a physicist at the University of Washington, used a torsion pendulum to measure the force between a gold-coated sphere and a flat gold-coated plate. The torsion pendulum is an exquisitely sensitive device that can detect forces millions of times smaller than the weight of a grain of sand. Lamoureux brought the sphere to within a fraction of a micrometer of the plate and measured the tiny force that pulled them together. His results agreed with Casimir's prediction to within 5%. It was the first unambiguous confirmation that Casimir's nearly 50-year-old prediction was correct. Since then, the measurements have been refined further. In 2002, a group at the University of Padua in Italy measured the Casimir force between parallel plates with even greater precision. Other groups have measured it using different geometries and different materials. The results consistently agree with the theoretical predictions. The Casimir effect is real. It's been measured. It's not a theoretical speculation or a mathematical artifact. It's a physical force that exists in the laboratory, arising from nothing more than the quantum properties of the electromagnetic field in its ground state. And here's what makes this remarkable. You can describe the Casimir effect using the language of virtual particles if you want to. You can say that the plates restrict the virtual photons between them, that fewer virtual photons can exist in the gap, and that this imbalance creates the force. This description, while not wrong in the mathematical sense, can be misleading because it makes you think the force is caused by tiny photon-like objects bouncing around between the plates. The more accurate description is that the plates alter the boundary conditions of the electromagnetic field, changing its ground state fluctuation spectrum, and this change in the field's ground state produces the force. No objects need to bounce around. The field itself, quiet as it is, does the work. Now let's move on to something even more precise, the Lamb shift. In 1947, Willis Lamb and Robert Rutherford performed an experiment that became one of the most important measurements in the history of physics. They measured the energy levels of the hydrogen atom with extraordinary precision, and they found something that existing theory couldn't explain. The experiment was performed at Columbia University in New York using microwave techniques that had been developed during World War II for radar systems. The war had driven rapid advances in microwave technology, and Lamb realized that this technology could be applied to fundamental physics. He was right. The precision of his microwave spectroscopy was far beyond anything that had been achieved before with optical methods. And that precision revealed a discrepancy that changed physics forever. To understand what they found, you need to know a little about hydrogen. Hydrogen is the simplest atom in the universe. It has one proton in the nucleus and one electron orbiting that proton. Because it's so simple, hydrogen has been the testing ground for quantum theories since the very beginning of quantum mechanics. If your theory can't predict the energy levels of hydrogen correctly, it's wrong. And if it can, that's strong evidence that it's on the right track. According to the Dirac equation, which describes the electron using both quantum mechanics and special relativity, certain energy levels of the hydrogen atom should have exactly the same energy. Specifically, two particular quantum states of the electron, called the 2s1/2 state and the 2p1/2 state, should be perfectly degenerate, meaning they should have identical energies. But Lamb and Rutherford found that these two states don't have the same energy. There's a tiny difference. The 2s1/2 state has slightly more energy than the 2p1/2 state. The difference is incredibly small, corresponding to a frequency of about 1057 megahertz, which is a microwave frequency. But it was unmistakably there, and the Dirac equation couldn't account for it. This tiny discrepancy, now called the Lamb shift, shook the foundations of theoretical physics. The Dirac equation was supposed to be the correct description of the electron. It had predicted the positron. It explained the fine structure of hydrogen beautifully. And yet, here was a measurement that it couldn't match. Something was missing. The answer came from quantum electrodynamics, from QED. The Lamb shift arises because the electron in the hydrogen atom doesn't just interact with the proton's electric field, it also interacts with the quantum vacuum. The electromagnetic field, even in its ground state, fluctuates at every point in space, including at the location of the electron. These vacuum fluctuations jostle the electron slightly, causing it to jitter around its average position. The electron doesn't sit perfectly still in its orbit. It shakes very slightly because the electromagnetic field it's embedded in is constantly fluctuating. This jittering affects the two quantum states differently. The 2s1/2 state, where the electron spends more time near the proton, is affected more by the vacuum fluctuations near the nucleus. The 2p1/2 state, where the electron spends less time near the nucleus, is affected less. The result is that the two states end up with slightly different energies. That difference is the Lamb shift. When Hans Bethe calculated this effect in 1947 using the new tools of QED, he got a number that matched Lamb and Rutherford's measurement. Not approximately, not roughly. He got a number that agreed with the measurement to within a few percent. The story of Bethe's calculation is famous in physics. He performed it on a train ride from Shelter Island, New York, back to Ithaca, where he worked at Cornell University. The Shelter Island Conference had brought together the leading physicists of the day to discuss the crisis created by Lamb's measurement. Beth, inspired by the discussions at the conference, worked out the calculation on the train using a technique called mass renormalization to handle the infinities that appeared in the mathematics. By the time the train reached Ithaca, he had the answer. It was the right answer. And as the theory was refined over the following years, as Feynman, Schwinger, and Tominaga developed the full machinery of renormalized QED, the theoretical prediction became more and more precise. The agreement between theory and experiment improved to 1 part in a million, then 1 part in a billion, then even better. Today, the Lamb shift has been measured and calculated to extraordinary precision. The agreement between the QED prediction and the experimental measurement is one of the most precisely verified predictions in all of science. And this prediction depends entirely on the vacuum not being empty. If you ignore the vacuum fluctuations, if you pretend that the electromagnetic field in its ground state is perfectly still, you get the wrong answer. The Lamb shift vanishes. The two states are perfectly degenerate. Only by including the effects of vacuum fluctuations do you get the correct result. This is powerful evidence that the quantum vacuum is physically real. It's not just a mathematical convenience or a philosophical interpretation. The vacuum fluctuations change the energy levels of atoms by specific calculable amounts, and those amounts match what we measure in the laboratory. The vacuum is doing something, it's having a physical effect on real atoms, and we can measure that effect with extraordinary precision. Now, you can describe the Lamb shift using virtual particle language if you choose. You can say that the electron is constantly emitting and reabsorbing virtual photons, and that these virtual photon interactions cause the energy shift. This is the standard textbook description, and in terms of the Feynman diagram calculation, it's accurate. The dominant Feynman diagram contributing to the Lamb shift involves the electron emitting a virtual photon, traveling a short distance, and then reabsorbing it. This diagram, when evaluated mathematically, gives the correct energy shift. But remember what we discussed earlier. The Feynman diagram is a bookkeeping tool. The virtual photon in that diagram is an internal line representing a mathematical term. The physical reality is that the electromagnetic field fluctuates in its ground state, and these fluctuations affect the electron's energy. The virtual photon is one way to mathematically organize this effect. It's not a tiny object that the electron literally spits out and swallows back up. There's another effect worth exploring because it provides yet another piece of evidence that the quantum vacuum has real physical consequences. It's called vacuum polarization. In classical physics, the electric field around a charged particle like an electron extends outward in all directions and gets weaker with distance according to Coulomb's law. The field is perfectly smooth and predictable. Nothing modifies it. Nothing gets between the charge and the field it produces. In quantum electrodynamics, things are different. The quantum vacuum affects the electric field itself. Here's why. The electron field fills all of space, even in the vacuum. It's there whether or not any real electrons are present. It's in its ground state, fluctuating quietly. When a charged particle like an electron creates an electric field, that field interacts with the electron field in the vacuum. The vacuum's electron field responds to the electric field by becoming slightly polarized. What this means is that the vacuum behaves a little bit like a dielectric material, like the insulating material between the plates of a capacitor. This might seem strange, the idea that empty space can behave like a material. But remember, space is not empty. It's filled with quantum fields, and those fields respond to disturbances, including the disturbance created by the presence of a charged particle. In a dielectric material, The electric field from a charge causes the molecules in the material to align slightly, positive sides toward the charge, negative sides away from it. This alignment partially screens the charge, making the effective field weaker at a distance. Something similar happens in the quantum vacuum. The electron field in the vacuum responds to the electric field of a charged particle in a way that partially screens the charge. The effect is that the electric charge of a particle appears slightly different depending on how closely you look at it. At large distances, the charge appears slightly weaker because the vacuum screening reduces it. At very short distances, closer than the screening cloud, the charge appears stronger, closer to its bare, unscreened value. Physicists call this the running of the coupling constant. The effective strength of the electromagnetic interaction changes with the energy scale at which you probe it. This is not a subtle effect that requires exotic experiments to observe. It's been measured directly in particle accelerator experiments. When electrons scatter off each other at low energies, the electromagnetic interaction has a certain strength characterized by the fine structure constant, approximately 1 over 137. But when the same scattering happens at very high energies, which corresponds to probing shorter distances, the effective strength of the interaction increases. The fine structure constant runs. It gets slightly larger at higher energies. At the energies reached by the Large Electron Positron Collider, which operated at CERN from 1989 to 2000, the effective value of the fine structure constant was measured to be about 1 over 128 instead of 1 over 137. The vacuum polarization effect changes the apparent strength of electromagnetism by about 7% at those energies. That's not a tiny correction. It's a substantial effect that has been measured with high precision, and it agrees perfectly with the QED prediction. If you use the virtual particle language, you describe vacuum polarization as being caused by virtual electron-positron pairs appearing in the vacuum near the charged particle, partially screening its charge. The virtual pairs act like tiny dipoles, with the virtual positron being attracted toward the real electron and the virtual electron being repelled. This creates a cloud of virtual polarization around every charged particle. Again, this description is mathematically valid. The relevant Feynman diagrams involve loops of virtual electron-positron pairs, and evaluating these diagrams gives the correct result. But the physical reality behind the mathematics is that the electron field in the vacuum responds to the presence of an electric field, and this response modifies the effective strength of the charge. The field interaction is what's real. The virtual pairs are the mathematical language used to calculate that interaction. I want to emphasize something important about all three of these effects: the Casimir effect, the Lamb shift, and vacuum polarization. They are not theoretical predictions waiting to be tested. They have been tested. They have been measured. They agree with the predictions of quantum field theory to extraordinary precision. These are established experimental facts, as solidly confirmed as anything in physics. The Casimir effect has been measured in multiple independent experiments using different techniques and different geometries. The results agree with theory. The Lamb shift has been measured to a precision of a few parts per million, and the QED prediction, calculated with vacuum fluctuations included, matches beautifully. Vacuum polarization has been measured at particle accelerators worldwide. The running of the fine structure constant matches the QED prediction precisely. These measurements tell us something profound. The vacuum is not empty. The quantum fields that fill space have physical effects even in their ground state. These effects are not large in everyday life. You don't notice the Casimir force when you walk through a room. The Lamb shift doesn't affect how your kitchen light works. Vacuum polarization doesn't change how a battery operates. The anomalous magnetic moment of the electron doesn't alter how your compass needle points. These are subtle effects that only become noticeable at very small distances or very high energies or in very precise measurements. They operate at scales far below anything you encounter in daily experience, in the realm of atoms and subatomic particles, at distances measured in billionths of a meter. But they're there. They're real. They've been measured repeatedly by independent groups around the world using different techniques and different equipment. And they confirm that the quantum vacuum is a physically active thing, not just empty space waiting for something to happen. There's another effect worth mentioning because it connects the quantum vacuum to something you might have seen in popular science: the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet. It has a property called a magnetic moment, which describes how strongly it interacts with the magnetic fields. The Dirac equation predicts a specific value for this magnetic moment, but the actual measured value is slightly different from the Dirac prediction. The difference, called the anomalous magnetic moment, arises from the electron's interaction with the quantum vacuum. The electron is constantly interacting with the fluctuating electromagnetic field around it. These interactions slightly modify its magnetic properties, making the electron a slightly stronger magnet than the Dirac equation alone would predict. The anomalous magnetic moment has been calculated using QED to extraordinary precision, and the result is one of the crown jewels of theoretical physics. The calculation is enormously complex. It requires evaluating thousands of Feynman diagrams, each one more intricate than the last. The most recent calculations involve diagrams with up to 5 loops, meaning 5 virtual particle loops in a single diagram. Evaluating these diagrams requires sophisticated computer algorithms and takes years of effort by teams of physicists and mathematicians. But the result is worth it. The QED prediction for the anomalous magnetic moment of the electron, including contributions from vacuum fluctuations calculated using thousands of Feynman diagrams involving virtual photons, virtual electron-positron pairs, and even virtual particles from other fields, agrees with the experimental measurement of better than 1 part in a trillion. Let me repeat that. 1 part in a trillion. The theoretical prediction and the experimental measurement agree to more than 12 significant figures. This is the most precise agreement between theory and experiment in the entire history of science. Nothing else in physics, in chemistry, in biology, in any science comes close to this level of precision. And this prediction depends entirely on including the effects of the quantum vacuum. Without vacuum fluctuations, the prediction is wrong. With them, it's the most accurate prediction humans have ever made. This level of agreement is not an accident. It's telling us something deep about the nature of reality. It's telling us that quantum field theory, with its fluctuating vacuum and its mathematical apparatus of virtual particles, captures something profoundly true about how the universe works. The mathematical framework may involve virtual particles as calculational tools, but the physical effects it predicts are absolutely real. The vacuum is not passive, it's not inert, it's not nothing. It's a dynamic, physically active state that affects real particles in measurable ways. There's something worth pausing to appreciate here. We started this journey by talking about empty space, about the void, about nothing. And we've ended up discovering that nothing is one of the most complex, subtle, and physically consequential things in the universe. The emptiest possible state of space, the best vacuum you could ever create, is teeming with physical activity, not with particles flying around, not with tiny objects popping in and out of existence, but with quantum fields fluctuating in their ground state, doing what the laws of physics require them to do, existing everywhere, always present, always active, and having measurable consequences that we can calculate and confirm in laboratories to precision levels that would have seemed like science fiction a century ago. The Casimir effect shows us that the vacuum exerts forces. The Lamb shift shows us that the vacuum changes the energy levels of atoms. Vacuum polarization shows us that the vacuum modifies the strength of electric charges. The anomalous magnetic moment of the electron shows us that the vacuum alters the magnetic properties of particles. All of these effects are real. All of them are measured. All of them arise because empty space is not empty. And all of them can be described using the language of virtual particles if you choose that mathematical framework. But that's a choice of language, not a revelation about tiny objects existing in the vacuum. The physics is about fields. The fields are real. The fluctuations are real. The effects are real. The virtual particles are the vocabulary of one particular way of calculating those effects. A powerful and useful vocabulary, to be sure, but a vocabulary nonetheless. So, where does this leave us? We know the vacuum has real physical effects. We know those effects arise from quantum field fluctuations in the ground state. We know the mathematics that describes these effects is extraordinarily accurate. And we know that the popular image of virtual particles as tiny objects appearing and disappearing in empty space is a metaphor that has been stretched well beyond its useful limits. But there are deeper questions to ask. What does it mean for our understanding of the universe that nothing is not nothing? What does it mean for cosmology, for the structure of space itself, that the vacuum carries energy and produces forces? And what happens to the vacuum in extreme conditions near black holes, in the early universe, in the most violent environments the cosmos has to offer? These questions take us from the laboratory to the edges of what we know about reality. And the answers, or in some cases, the absence of answers, reveal that the quantum vacuum is not just a curiosity of atomic physics. It's one of the deepest mysteries in all of science. We've now seen that the quantum vacuum is not empty, that virtual particles are mathematical tools rather than tiny objects, and that the vacuum has real, measurable physical effects confirmed by experiment. But all of this raises a much deeper question, a question that takes us from laboratory physics to the very structure of the universe. If the vacuum is not nothing, if it's the ground state of quantum fields that fill every point in space, and if that ground state has physical consequences, then what does this mean for the universe as a whole? What does it mean for our understanding of reality at the larger scales? Because here's the thing. If quantum fields fluctuate everywhere, even in their lowest energy state, then every point in space has some minimum amount of energy associated with those fluctuations. We talked about 0 point energy earlier, the irreducible energy that remains even at absolute zero. Even when everything is as quiet as quantum mechanics allows, the fields still jitter, and that jitter carries energy. Not a lot at any single point, but space is big. If every cubic centimeter of space carries even a tiny amount of vacuum energy, then across the entire observable universe, that energy adds up to an enormous total. This idea, vacuum energy filling all of space, connects directly to one of the biggest mysteries in modern physics. It connects to something called the cosmological constant and the mismatch between what quantum field theory predicts and what astronomers observe is so extreme that it has been called the worst prediction in the history of physics. Let me explain. In 1917, Albert Einstein added a term to his equations of general relativity. He called it the cosmological constant, and he represented it with the Greek letter lambda. Einstein introduced this term because he believed the universe was static, neither expanding nor contracting. Without the cosmological constant, his equations predicted that the universe should be either expanding or collapsing under its own gravity. A static universe seemed to be what observations at the time suggested. So Einstein added the cosmological constant as a kind of anti-gravity term, a repulsive force that could balance gravity and keep the universe stable. When Edwin Hubble discovered in 1929 that the universe is in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder. He removed it from his equations and moved on. For decades, most physicists ignored the cosmological constant. It seemed unnecessary. The universe was expanding, and you didn't need a cosmological constant to describe that. But in 1998, two independent teams of astronomers made a stunning discovery. They were studying distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances. What they found was that the expansion of the universe is not slowing down, as everyone expected it would under the pull of gravity. The expansion is accelerating. Something is pushing the universe apart faster and faster. The galaxies are not just moving away from each other, they're moving away from each other at an increasing rate. This discovery, which earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, brought the cosmological constant roaring back. The accelerating expansion could be explained if space itself carried a small but positive amount of energy, a vacuum energy that acts as a repulsive force on cosmic scales. Einstein's cosmological constant, the term he had dismissed as a blunder, turned out to be real. So far, so good. Quantum field theory predicts that the vacuum has energy. Astronomical observations show that space has energy that's driving the accelerating expansion. These two ideas should fit together perfectly. Quantum field theory should predict the amount of vacuum energy, and that prediction should match what astronomers measure. It doesn't. Not even close. Not even in the same universe of close. When physicists use quantum field theory to calculate the energy density of the vacuum, the amount of energy per cubic centimeter of empty space, they get a number that is staggeringly large. The exact number depends on the assumptions you make about how to do the calculation, particularly on what energy scale you cut off the calculation, because without a cutoff, the answer is infinite. But using reasonable assumptions, cutting off the calculation at the Planck energy, which is the scale where quantum gravity effects are expected to become important, the predicted vacuum energy density is about 10 to the power of 113 joules per cubic meter. The observed vacuum energy density, measured from the accelerating expansion of the universe, is about 10 to the power of negative 9 joules per cubic meter. The prediction is wrong by a factor of 10 to the power of 122. That's a 1 followed by 122 zeros. This isn't a small discrepancy that can be explained by rounding errors or imprecise measurements. This is the theoretical prediction overshooting the observed value by 122 orders of magnitude. It is, by any measure, the largest disagreement between theory and observation in the entire history of science. To put this in perspective, the difference between the size of an atom and the size of the observable universe is only about 36 orders of magnitude. The vacuum energy discrepancy is more than 3 times larger than the ratio between the smallest and largest things we know of. If your prediction of the distance from your house to the grocery store was off by this factor, you would calculate a distance larger than the observable universe. Not just a little wrong, catastrophically wrong. This is called the cosmological constant problem, and it is widely considered one of the deepest unsolved problems in all of physics. It's not just that we can't calculate the vacuum energy correctly. It's that our best theory of particle physics, quantum field theory, which predicts the Lamb shift and the anomalous magnetic moment of the electron to 12 decimal places, gives an answer for the vacuum energy that's wrong by 122 orders of magnitude when applied to cosmology. Nobody knows why. There have been many proposals. Some physicists suggest that some unknown symmetry cancels most of the vacuum energy, leaving only the tiny residual amount we observe. Supersymmetry, a theoretical framework that proposes a partner particle for every known particle, would partially cancel the vacuum energy, but supersymmetry would need to be an exact symmetry for the cancellation to work perfectly. And we know supersymmetry is not exact because we haven't found any of the partner particles in experiments at the Large Hadron Collider. Broken supersymmetry reduces the vacuum energy but doesn't come close to solving the problem. Other physicists have proposed that the cosmological constant is not really vacuum energy at all, but something else entirely. A new form of energy called dark energy that mimics the effects of a cosmological constant but has a different origin. Maybe dark energy is a slowly evolving field, sometimes called quintessence, that fills space and drives the accelerating expansion. But so far, all observations are consistent with a simple cosmological constant. There's no evidence that dark energy changes over time. Still, others invoke the anthropic principle. They argue that in a multiverse with many different regions of space, each with a different value of the cosmological constant, most regions would have vacuum energies so large that galaxies, stars, and life could never form. We happen to live in a region where the vacuum energy is small enough for structure to develop. This isn't really an explanation in the scientific sense. It's more of an observation that we could only exist in a universe where the conditions allow our existence. Many physicists find this unsatisfying because it doesn't tell us anything about the underlying mechanism. The cosmological constant problem remains open. It's one of the biggest clues we have that something fundamental is missing from our understanding of physics. Quantum field theory works brilliantly at the scale of atoms and particles. General relativity works brilliantly at the scale of planets, stars, and galaxies. But when you try to combine them, when you try to ask what the quantum vacuum does to the large scale structure of the universe, the two theories give widely inconsistent answers. This suggests that there's a deeper theory, a theory of quantum gravity that we haven't found yet. A theory that would reconcile quantum field theory with general relativity and, presumably, solve the cosmological constant problem along the way. Now, let's shift our attention to what happens to the quantum vacuum under extreme conditions. Because the vacuum doesn't just sit there quietly in all circumstances. Under the right conditions, the quantum vacuum can be provoked into producing real particles, genuinely real, detectable, measurable particles that didn't exist before. And understanding how this happens will help us appreciate the difference between the quiet fluctuations of the ground state and actual particle creation. The most famous example is called the Schwinger effect, named after Julian Schwinger, who predicted it in 1951. Schwinger showed that if you apply an extraordinarily strong electric field to a region of empty space, the vacuum will produce real electron-positron pairs, not virtual pairs, real ones, detectable particles that fly apart and can be captured by instruments. Here's the physical picture. The electron field fills all of space, even in the vacuum. Normally, the field is in its ground state, fluctuating quietly. But when you apply an extremely strong electric field, you're putting energy into the system. The electric field does work on the electron field. And if the field is strong enough, it can pump enough energy into the electron field to create real excitations, real electrons and real positrons. Think of it this way. Creating a real electron-positron pair requires a minimum amount of energy, at least twice the rest mass energy of an electron, because you need to create both the electron and the positron. That's about 1.02 million electron volts of energy. In everyday circumstances, the electromagnetic field in the vacuum doesn't have anywhere near this much energy concentrated in a small enough region to create particles. The vacuum fluctuations are far too weak. But if you apply an enormous external electric field, you're adding energy to the system. If that field is strong enough, roughly about 1.3 times 10 to the 18th volts per meter, which is called the Schwinger limit, the energy density becomes sufficient to rip real electron-positron pairs out of the vacuum. The Schwinger effect has never been observed directly because the electric fields required are fantastically strong. The Schwinger limit is roughly 1 million times stronger than the strongest electric fields we can currently produce in laboratories, even with the most powerful focused lasers. But physicists expect that as laser technology advances, producing ever more intense electromagnetic fields, the Schwinger effect might eventually be observed. Several major laser facilities around the world, including the extreme light infrastructure in Europe, are working toward intensities that could approach the Schwinger limit. What's important for our discussion is what the Schwinger effect tells us about the relationship between the vacuum and particles. The vacuum is not creating something from nothing. The energy for the particle creation comes from the external electric field. The field does work on the quantum vacuum, pumping energy into the electron field until real excitations are produced. The particles come from the field. The energy comes from the external source. Nothing is created from nothing. Nothing is borrowed from nowhere. The process obeys conservation of energy completely. This is a crucial distinction that popular accounts often get wrong. You'll sometimes hear that the vacuum creates particles from nothing, that energy is borrowed from the vacuum and paid back later, or that the uncertainty principle allows energy to appear from nowhere as long as it disappears quickly enough. None of this is accurate. The uncertainty principle does not allow energy to be created from nothing. It says that energy cannot be measured with perfect precision over very short time intervals. That's a statement about measurement and definition, not about creation. The vacuum fluctuations are not energy being created and destroyed. They're the irreducible quantum jitter of fields in their ground state. When real particles are created from the vacuum, as in the Schwinger effect, the energy always comes from somewhere. There's always an external source, whether it's an intense electromagnetic field, a gravitational field, or some other form of energy input. The vacuum provides the field that gets excited, but it doesn't provide the energy for free. This brings us to one of the most famous and dramatic predictions in all of physics: Hawking radiation. In 1974, Stephen Hawking published a paper showing that black holes are not perfectly black. They emit radiation. They glow very faintly, and over enormous spans of time, they slowly evaporate, losing mass and eventually disappearing entirely. This was a shocking prediction because black holes were supposed to be objects from which nothing could escape. The gravitational pull of a black hole is so strong that even light can't get out. So, how could anything be emitted? Hawking's analysis showed that the extreme gravitational field near the event horizon of a black hole affects the quantum vacuum in a way that produces real particles. The mechanism is subtle and mathematically involved, but the essential idea is this: the event horizon of a black hole is a boundary in space-time. On one side, space is normal. On the other side, space is falling inward faster than light can travel outward. This boundary creates a situation where the definition of what counts as a particle changes depending on where you are and how you're moving. An observer far from the black hole and an observer falling into the black hole disagree about the state of the quantum fields. What looks like the vacuum state to the falling observer does not look like the vacuum state to the distant observer. The distant observer sees particles, real particles, thermal radiation with a specific temperature related to the black hole's mass. Now, you've probably heard Hawking radiation described in terms of virtual particle pairs. The popular account goes something like this: a virtual particle antiparticle pair pops into existence near the event horizon. One particle falls into the black hole while the other escapes. The escape particle becomes real, and the black hole loses a tiny amount of mass to compensate. This description is vivid and memorable, and Hawking himself used a version of it in his popular writings. But this description is misleading in several ways. First, as we've discussed, virtual particles are not tiny objects that pop into existence. They're mathematical terms in perturbation theory calculations. The image of a virtual pair appearing near the event horizon is a cartoon, not a physical description. Second, Hawking's actual calculation doesn't involve virtual particles at all. It involves analyzing how the quantum state of a field is perceived differently by different observers in curved spacetime. The mathematics is about field modes and Bogoliubov transformations, not about virtual particle pairs splitting apart. Third, the popular description makes it sound like energy is being created from nothing, with one particle carrying positive energy and the other carrying negative energy that reduces the black hole's mass. In reality, the energy for Hawking radiation comes from the gravitational field of the black hole itself. The black hole's mass decreases because its gravitational energy is being converted into the energy of the emitted radiation. Energy is conserved throughout the process. Nothing comes from nothing. Hawking radiation has never been directly observed from an actual black hole because the effect is incredibly small. For a black hole with the mass of the sun, the Hawking temperature would be about 60 billionths of a Kelvin above absolute zero. That's so cold that it's completely overwhelmed by the cosmic microwave background radiation, which has a temperature of about 2.7 Kelvin. To observe Hawking radiation directly, You'd need a black hole much smaller than any that are known to exist, or you'd need instruments of a sensitivity far beyond anything currently possible. However, analogues of Hawking radiation have been observed in laboratory systems. In 2016, Jeff Steinhauer at the Technion in Israel reported observing the acoustic analog of Hawking radiation in a system of ultra-cold atoms. The system mimics the properties of a black hole's event horizon using sound waves instead of light, and Steinhauer observed the thermal radiation that Hawking's theory predicts. While this is not the same as observing radiation from an actual black hole, it provides compelling evidence that the underlying physics is correct. The early universe provides another context where the quantum vacuum played a dramatic role. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. The energy densities were so extreme that quantum field effects dominated. During a period called cosmic inflation, which is thought to have occurred within the first 10 to the negative 36 seconds after the Big Bang, the universe expanded exponentially, doubling in size roughly every 10 to the negative 37 seconds. In an incredibly brief span of time, the universe expanded by a factor of at least 10 to the 26th, turning a region smaller than an atom into something larger than the observable universe today. During inflation, quantum vacuum fluctuations were stretched to cosmic scales by the rapid expansion. Fluctuations that were originally microscopic, operating at subatomic length scales, were expanded to enormous sizes spanning millions of light years. These stretch fluctuations became the seeds of all the structure we see in the universe today. Every galaxy, every cluster of galaxies, every void, every filament in the cosmic web ultimately traces its origin to quantum fluctuations in the vacuum during inflation. We can see the imprint of these primordial fluctuations in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe. The cosmic microwave background has tiny temperature variations, about 1 part in 100,000, from one direction to another. These variations were mapped with extraordinary precision, first by the COBE satellite in 1992, then by WMAP starting in 2001, and most recently by the Planck satellite, which released its final results in 2018. The pattern of these variations matches what inflationary theory predicts from quantum vacuum fluctuations. The statistical properties of the fluctuations, their amplitude, their scale dependence, their Gaussian distribution all match the theoretical predictions. This is perhaps the most dramatic consequence of the quantum vacuum. The tiny random fluctuations of quantum fields in the very early universe, amplified by the rapid expansion of inflation, became the seeds from which all cosmic structure grew. The galaxies exist because the vacuum fluctuated. The stars exist because the vacuum fluctuated. The planets exist. You exist. Because quantum fields in their ground state jittered randomly in the first tiny fraction of a second after the universe began. Let me bring all of this together now. Because we've covered a lot of ground and I want to make sure the central message is clear. We started with a simple question. What is a virtual particle and why is an empty space empty? The answer turns out to be deeper and more surprising than most people expect. So here's what we've learned, not as a list of facts, but as a single coherent picture of reality. The universe is not made of objects scattered through emptiness. It's made of fields, continuous, everywhere present quantum fields that cannot be switched off or emptied out. Particles are what those fields do when they're excited. And even when they're not excited, even in their absolute quietest configuration, those fields still hum with an irreducible minimum of activity dictated by the deepest laws of quantum physics. That hum is the vacuum. That hum is what we used to call nothing. And the virtual particles you've heard so much about are not hidden inhabitants of that hum. They are the vocabulary of one powerful mathematical language that physicists invented to describe what the hum does when it interacts with matter. Change the mathematical language, and the virtual particles change or vanish entirely. But the hum remains, the fields remain, the physical consequences remain. The math is a lens we built. The fields are what's actually there. The lens is extraordinary, precise enough to predict experiments to 12 decimal places. But the lens is not the landscape. The fields are the landscape. And that landscape stretches across every point in the universe, active and alive, even in the deepest silence of empty space. But the phenomena that virtual particle calculations describe are absolutely real. The effects we explored earlier, the force between metal plates, the shifted energy levels, the screened charges, the magnetic properties of electrons, none of these are theoretical curiosities. They are bedrock experimental facts, and every single one of them depends on the vacuum being physically active. What ties them together is not a catalogue of separate phenomena, but a single unifying truth. The quantum fields never rest, and their restlessness shapes everything they touch. The virtual particles used to calculate these effects are mathematical tools, but the fields those tools describe are absolutely real. The quantum vacuum also connects to some of the deepest unsolved problems in physics. The cosmological constant problem, the mismatch between the predicted vacuum energy and the observed vacuum energy, is off by 122 orders of magnitude. This is widely considered the worst prediction in the history of physics and suggests that something fundamental is missing from our understanding of how quantum field theory and gravity fit together. Solving this problem might require a theory of quantum gravity that we haven't discovered yet. Under extreme conditions, near black holes or in the early universe, the quantum vacuum can be provoked into producing real particles. But this always requires an external source of energy. The vacuum does not create something from nothing. When Hawking radiation is emitted from a black hole, the energy comes from the black hole's gravitational field. When the Schwinger effect produces electron-positron pairs, the energy comes from the applied electric field. When inflation stretched vacuum, fluctuations into the seeds of cosmic structure, the energy came from the inflaton field driving the expansion. The vacuum provides the fields. The energy comes from elsewhere. Conservation of energy is never violated. What does all this mean for how we should think about reality? It means that the universe is far richer and stranger than our everyday experience suggests. The emptiest place you can imagine, the most perfect vacuum you could ever create, is not empty. It's alive with the quiet activity of quantum fields, not alive with particles, not alive with tiny objects flickering in and out of being, but alive with fluctuations, with the irreducible quantum hum of fields that fill every point in space and time. It means that the division between something and nothing is not as sharp as we might think. Nothing, in the deepest physical sense, is not the absence of everything. It's the lowest energy state of everything. All the fields are still there. All the interactions are still possible. The potential for every particle that could ever exist is encoded in those fields, waiting for enough energy to bring it forth. The vacuum is not a void, it's a sea of potential. And it means that some of the most important discoveries in physics, from the precise energy levels of hydrogen to the large scale structure of the cosmos, depend on understanding what nothing really is. The vacuum is not a footnote in physics, it's central. It shapes the behavior of every particle. It contributes to every interaction. It seeded the formation of every galaxy. It drives the accelerating expansion of the universe. Nothing is everywhere, and it does everything. There's something profound and humbling about this. For thousands of years, humans looked at empty space and saw nothing. We thought the void was simple, featureless, inert. It took centuries of careful observation, brilliant theoretical insight, and extraordinarily precise experiments to reveal the truth. The void is not simple. The void is one of the most complex and fascinating things in the universe. It's a dynamic state of quantum fields with measurable physical properties and consequences that reach from the subatomic to the cosmic. When you look out at the night sky, at the dark spaces between the stars, you're not looking at nothing. You're looking at quantum fields in their ground state. You're looking at the electromagnetic field, the electron field, the quark fields, the neutrino fields, all of them present, all of them fluctuating, all of them quietly humming with the minimum energy that the laws of quantum mechanics demand. That darkness between the stars is not empty. It's full, full of fields, full of potential, full of the quiet machinery that makes the universe work. The next time someone tells you that empty space is filled with virtual particles popping in and out of existence, you'll know what lies beneath that shorthand. You'll know the deeper story. It's not about objects appearing and vanishing. It's about fields. Fields that fill every point in the universe. Fields that are always there, always active, always fluctuating in their ground state. Fields that push metal plates together, shift the energy levels of atoms, modify the strength of electric charges, seeded the formation of galaxies, and drive the accelerating expansion of the cosmos. Fields that make nothing one of the most interesting things in all of physics. The vacuum is not empty. Virtual particles are not what you thought they were. And nothing, it turns out, is really something extraordinary. That's not just a clever turn of phrase. It's one of the deepest discoveries in the history of science. The universe is stranger, richer, and more beautiful than we ever imagined, all the way down to the very nature of nothing itself. Thank you for joining me on this journey into the heart of the quantum vacuum. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the strangest and most wonderful ideas in physics. And the next time you find yourself standing in a quiet, empty room, remember that the room is not empty. It's filled with quantum fields, humming quietly in their ground state, making the universe possible. Good night, and may you never think about nothing the same way again.